Okay, now we've got the memory stuff out of the way and the general why we're using GPUs part out of the way, which is necessary, I think, for us to start thinking about actually writing our own GPU code. So that's going to be the focus of, well, for the next day and a half, is how to write GPU code. So we're going to start by looking at defining some terms, kernels and threads. You've already heard me say the word kernel quite a few times, and threads a few times as well, so let's actually try to figure out what these mean, particularly in the context of working on the GPU. So threads are independent streams of execution, and they run simultaneously on the GPU. So you can think on the GPU, we've got lots of work being done in parallel, and each bit of work is being done by a thread. But what work are they doing? The work we call a kernel. Well, the terminology I use is, this is the context that I use a kernel. So you can think of as a kernel is the function that's being run by each thread. It's the work being done by each thread. And if we want to implement an algorithm or a kernel in parallel, we write the kernel that expresses this, the work that a single thread would do, and then we launch many threads running the same kernel, and together they solve the problem. So CUDA provides language support for writing kernels. So we're going to see that in a moment. You can write down a function that describes the work you want an individual thread to do, and then you can put a little bit of a syntactic sugar on it to say, this is a kernel. This is something that we're going to run on one thread of the GPU. And then it provides a syntax for launching kernels, many threads on the GPU. So it provides a syntax where you can say, okay, here's the kernel, now run it on this many threads on the GPU. So you'll run it on however many threads you need to solve your problem. So CUDA hides a lot of the low-level details of launching threads. We've already seen a bit in the profiling example before that there was this function called CUDA launch. And CUDA launch will take the parameters, like the value of n and x and y pointers that you passed in on the host, and it'll package them up into a little bit and copy them over to the GPU and set the GPU up to actually run the kernel. You don't have to worry about that. The CUDA runtime looks after all of that for you. You just have to use these language extensions to describe your kernels and launch them on threads. So roughly speaking, the process for developing a CUDA kernel, once you've got like a function, for example, matrix multiplication, that you've decided you want to write a kernel for, the first thing you do is you formulate it in terms of parallel work items. Then you write a kernel that implements each, once you've got this described as, well, here's the work item I want to be done by a single thread, and they have to work together to solve this, you write that kernel for that single work item, and then once you've got that, you launch the kernel with the required number of threads. I haven't put the printf debug loop in here, but it's implicit. And I just want to take a little detour here and say people often say CUDA is hard, and what they mean is parallel programming is hard, because you see the first step here is to formulate what you're trying to do as a parallel task in parallel work items. And that's the hard bit. It's one thing to say, I want to do matrix multiplication and implement a nested, triply nested for loop. That's not too hard, to describe your algorithm. But then if you want to express how to do that in parallel, that's where it becomes a bit more difficult. And you'll find that if you want to also express this efficiently in parallel for a multi-core processor, there's a lot more work involved. It's not just writing a triply nested loop. So I think, but the big benefit of working with something like CUDA, which forces you to express parallelism up front and explicitly, is that you get the hard part out of the way at the start, or you make design decisions based on how to make things parallel. You make those difficult decisions, design decisions, and that just difficult programming work at the start. So we looked at this example. We looked at the cuBLAS DAXB before. which was this what I called vector addition, and we're going to, so we called cuBLAS before, now we're going to implement our own version of this. This is what we're going to work on for the next few slides. So what is this AXP operation? It's short for AX plus Y, because remember this was back in the 60s they came up with this, so they apparently, yeah, there was a premium on, you wanted to make things as short as possible, so they abbreviated things very heavily, but this means AX plus Y, and it means if we have two vectors of length n, two arrays of length n, we store in Y, we store Y, the original value of Y, plus alpha times X, where alpha is some constant, is a scalar value. So when you break this down, if you start thinking in parallel terms, you write it down something like this. You know, each value, output value in Y is equal to the original value in Y plus alpha, or A, times the corresponding value in X. And this is very nice for a parallel implementation because we can calculate all of these values independently. You know, to calculate the value at x0, I don't need to know the value that's calculated at x6, and vice versa. So we can do this completely independently. We can break it up into n independent bits of work that can be done, and there's no need to synchronize or coordinate between threads to do this. Now, if we were to implement this on the CPU with a loop, I'm sure we've all seen something like this. You know, we have a function that takes in a pointer to the data we're going to be modifying, to the x and the y, sum the value for a and the length. And then we have a for loop, you know, for I equals 0 up to n minus 1, calculate the value for value I. So this is inherently a sequential operation. It's not a parallel. This here, as it's written, is a sequential operation. That's what a for loop is. It says, you know, do it for value for I equals 0, then do it for I equals 1, then do it for I equals 2. But this is something that we could easily express in parallel. So if we wanted to express this same loop here in a parallel kernel, a loop here we have in a parallel kernel, we end up with something that looks like this. So what is a kernel? A kernel really defines the work that's going to be done by a single thread. And the combined output, the combined work, in this case adding some vectors together, will be performed by many threads executing the same kernel simultaneously. And this corresponds to the inner part of the loop for a BLAS1 operation like AXP. So here's some code for adding two vectors. It's a little bit simpler than the AXP just because I wanted to fit them side by side on a slide and keep it as simple as possible. So here we have a loop, add CPU, which takes an A and a B and a length and adds them together and puts them back into A. Here's what the kernel to do this looks like on the GPU. So you can see it looks very similar. It's got the same call signature. You know, he takes in the pointers to A and B and a length n. And then this part here looks just like the inner part of the loop here, but we don't have an explicit loop anymore. What we've got is we have to calculate this index I, because you can imagine if we have launched a bunch of threads and said, you've all got to do the same kernel to solve the problem, each thread is going to have slightly different work to do. In this case, each thread is going to be assigned one value that it has to calculate and store in the output vector. And so each thread is given a thread index. So this thread IDX here, this is a magic variable. This is just this is something that's provided by CUDA. And when you're inside a kernel, you can call this threadidx.x, and that will tell you what your thread number is. So we'll see in a bit, if you launch 1,000 threads, 1,000 threads will be launched, and then each one can ask, which thread number am I? And then once it knows what thread number it is, it knows exactly which bit of work to go and do. Or you basically have to tell it which bit of work to do, which here is trivial, because we're just, take that index and then use it to load some values and write a value. So we've replaced the for loop here with, we get our index like this. And the other difference is we've now stuck this underscore underscore global underscore underscore in front of the function. This is saying, yes?
Why would we need the n in the GPU function?
Sorry?
Why would we need the n, the maximum counter, in the GPU kernel?
That's a very good question, and we're going to see that in a moment. Yes, that's because we don't use it here, but we're going to see, and we don't actually need it in this example, but turns out you do. So we also have this global keyword here, which is saying that this is a kernel. So when the NVCC gets the input file, it has to decide which bits am I going to compile for the GPU and which bits am I going to compile for the CPU. And this global keyword is basically telling NVCC, okay, this is a kernel. Okay, so any more questions? Yes?
So the global is only then valid for the next function that comes afterwards?
Yeah, so you have to annotate each function, or each kernel, I should say, because they use a function syntax, but they're a kernel.
So the number of threads should be equal to n?
Yep, exactly. And the reason why we need the n, as we're going to see in a bit, is that normally you launch threads in blocks of like groups of 128 or 512 or whatever. So sometimes you'll have some threads at the end which don't actually have to do work, and you've got to check on this.
And I can't change it.
Sorry?
It should be equal to n. I can't change it. I can't make less thread.
Yeah, well, yeah, we're going to see. We'll see exactly how that works in a bit. So this is the first half of the challenge, right? We've created our kernel, but we've still got to launch the kernel. We've got to actually make it go and do some work. And launching a kernel is the next bit of nice syntactic sugar that CUDA gives us. So when you want to launch a kernel or you want to run some work on the GPU, in your CPU host code, at some point you'll have a bit of code that says launch the kernel, launch the kernel. And they have this triple chevron, what they call a triple chevron syntax, less than, and greater than, which turns out was a terrible choice, but for various complicated C++ passing reasons, but that's the decision they made. So for launching a kernel. So if we look at our example for adding 2 vectors on the host, we might set n equals to 1024, allocate some memory, and then do the addition. Here, it looks very similar. N equals 1024. Now we do some allocation on the device, or we allocate some managed memory, whichever you prefer. And then we call the add GPU with the same arguments as before. However, we've got this bit here inside this CUDA launch syntax. Because remember, we annotated add GPU as being a device function. So if you try to call this just like you call this without this extra information, you'll get a compile time error saying, this is a kernel. You can't just launch a kernel. Like, you've got to actually give me a launch specification. So here we can see that we're launching the kernel with a 1, a comma, n. Later on, we're going to learn what this 1 means. But for the time being, the number of threads that we want to use is the second argument when we launch it. So we're saying, take this kernel and run it on num threads on the GPU. And here are your arguments. Any questions?
What's the first 1? Why is it 1 comma?
We're going to get to that in a bit. That's basically the next section. That's the number. Let's just wait on that. So we're going to now do an exercise called My First Kernel, where we actually get to write a kernel. So we've got this. This is the add GPU we did here was a slightly simplified version of AXPI. Let's go ahead and actually implement that kernel. So if we load up this, if you open up this file, you'll find at the top of the file there's a to-do asking you to implement the kernel. And then later on, so because remember there's two parts, you've got to define the kernel and then you've got to launch it. So just look for the to-dos, they'll show you where to go. And then compile it and run. And then what I would like people to do is to try out vectors of different sizes. So I would start with passing in 8. So that's 200, that'll be 2 to the power 8, which is 256. And play around with what happens as you change the size of the input. Okay, and step number 4 is probably a hint about what's going to happen. Any questions?
So from your extra point, I guess that kernel code fully supports templates.
Sorry?
Does kernel code support templates?
Yes. Yes, so that's a good question. You can do all of C++11 stuff is features and C++ features are available in CUDA. It's not like OpenCL, which is a very limited subset. There are some things you can't do. You can't have virtual function calls on a GPU because when you think about it, you realize, and when you understand how the GPU works underneath the hood, they don't make sense. But you can use all of your favorite template metaprogramming problems. I don't know if that techniques. I don't know if that's a good thing or a bad thing, but you can use them here.
I think this question was already asked before. Why are we passing end to the function again?
Okay, the question was, why are we passing n to the function again? And the answer is, you're going to find out soon. Don't worry, that's in the next part. And I think once you've played around with the sizes here, when in part number 3, you'll start to get an inkling about why. You'll start to have a feeling about why that is. Okay, and the scheduled coffee break is 5 minutes from now, so I would suggest that people can hack away on this. You can go grab a coffee. We're going to take our time working on this. So you can start up, you can grab a coffee, have a talk.